So we've learned there are two kinds of improper integrals. There are type 1, where we're integrating from some number to infinity, or minus infinity to some number, or minus infinity to infinity. And we evaluate them by taking a limit. Or there are improper integrals of type 2, where we have some vertical asymptote, and we have to integrate by approximating that point where there is a vertical asymptote with a limit. The procedure is, well, at least the philosophy behind it is very similar. Technicalities are a little bit different kinds of singularity. The key thing we learned last time was that 1 over x is the cutoff, is the point for both. So if we have an improper integral of type 1, then 1 over x is not decaying fast enough in order for the area underneath the graph to be finite. But 1 over x to the p, for p bigger than 1, actually is decaying fast enough. And if the integral is finite, we say the thing converges. Okay, that's type 1. Type 2, which are a bit harder, is where we have a vertical asymptote. So if we consider one of the simplest cases, 1 over x, from 0 to 1. In this case, 1 over x is blowing up too fast as we approach 0 to allow there to be a finite integral. So there's infinite area underneath the graph from 0 to 1, where the graph is 1 over x. Yeah? But again, it's the cutoff point. But this time, in order for this thing to be finite, we need the singularity not to blow up too fast. Right? So if we think about what that requires, that means we need a singularity to be blowing up like 1 over x to the p, right? But now p has to be between 0 and 1. Because as we talked about last time, if we have 1 over x to the p, where p is between 0 and 1, since if we take a root of a number x between 0 and 1, the root is bigger. Yeah? Therefore, 1 over x to the p is blowing up less quickly, and it turns out it blows up sufficiently less quickly in order for there to be a finite area underneath the graph. So when we think about these questions, the first thing we'll do is to look at the growth, either the growth towards infinity for type 1 or the growth upwards towards infinity as you approach the singularity in type 2, and ask ourselves, is it in this case blowing up faster or equal to 1 over x? In this case, is it decaying more at the rate of 1 over x or more slowly? If it's decaying at the rate of 1 over x or more slowly, then for sure it cannot have finite integral, it cannot converge. If it's blowing up at the rate of 1 over x or faster, then it cannot converge. All right, give me a thumbs up if that is making sense to you. Okay, cool. All right, so let's try one of these. So I did a couple more examples after the class ended last time. If you haven't seen those, please watch those, because I'm only going to do different examples going forward. Let's do this. Example 2. Let's consider this. Okay, so before we do the calculation, we could try and understand whether or not we believe this thing is going to have a finite integral or not. All right, so look at this. What do we have? We have something which we're integrating from minus infinity to 0. Right? So let's say this here is 0. And as you can see, it's definitely decaying, right? Because as x tends towards minus infinity, e to the x is getting very, very small, right? It's getting very, very small, and it's killing this x, which is becoming more and more negative, right? So we do expect this thing to be going down to 0. The issue is it going down to 0 fast enough? Yeah. So what do you think? Do you think this thing will converge? All right, let's look at this guy. So what do we know about e to the x? E to the x is the fastest growing function we have, right? At least the fastest growing elementary function. It is insanely fast growing. It is so fast growing that our brains do not naturally register how quickly it grows. This is one of the really important phenomena of the influence of maths in the real world, is that e to the x appears in many places and people don't naturally understand how quickly it grows. Right? So e to the x grows like this, and for negative x, e to the x is 1 over e to the x, which is decaying just as fast as e to the x, for positive x is growing, right? So e to the x, where x is negative, is flattening down to 0 at an incredible rate, yeah? At an absolute incredible rate. So the fact that we have an x in front, which is getting more and more negative as we go towards negative infinity, is not affecting how dramatically this thing is going down to 0. So we would actually expect this thing to converge, yeah? If we just rewrote this as an integral from 0 to infinity and we had minus x e to the minus x, probably that would look more natural to you, right? So if we just did this solution, just by changing variable from x to, say, minus y, then we would have this integral from 0 to y minus y e to the minus y, to infinity, sorry, dy, right? And then that looks like 0 to infinity minus y over e to the y. And maybe that makes it look more clearly converging, because now we have that y is positive, yeah? And this thing is becoming more negative, but it's being killed by how quickly e to the y grows. Do you see what I mean? So this thing actually will converge, you know? And given that it converges, we should be able to calculate it. So let's see what the answer actually is. So star is equal to the limit as r goes to negative infinity of the integral from r to 0, x e to the x dx, like this, right? And what's the natural method to try and understand this? What technique would we use to calculate this? Integration by parts, right? Because it's a classic integration by parts problem. We have an x and e to the x, right? And we know if we differentiate the x, it goes down to 1, it becomes easier. If we integrate e to the x, it's still e to the x, it becomes no worse. So when you use integration by parts, we are going to let u be the x and v prime be the e to the x. Yeah. And what do we have? 0 to r, then we have u. Oops. I'm going to have x e to x like this. This is the uv. And then minus, let's put brackets here, integral from to 0. We differentiate this guy, we integrate this guy, we just get e to the x like this. X, and that's our guy. Then we can just evaluate this thing. The limit as r goes to infinity. And what do we have? So sticking 0 into this, we're just going to get 0. So we're just going to have minus e to the r from this part right here. Yeah. And then what's this thing? This is, let's put the antiderivative here, 0 to e to the x. So this is the limit as r goes to infinity, minus r e to the r, minus, put 0 inside this, we're going to get 1. And then we put r into this, like this. So what's this in total? Let's just take out the brackets. So this is the limit as r goes to infinity of minus r e to the r minus 1. Let's put this thing here, plus e to the r, and then minus 1, like this. Yeah? So what's that limit? What's the limit of this as r goes to infinity? Yes. Sorry. Typo. Thank you. There we go. All right. What's the limit of that thing? Indeed, minus 1. Because as r goes to negative infinity, this e to the minus r, as just talked about, is going to 0 incredibly fast. It's killing this term. Yeah. If you really need to, you can do L'Hopital's rule, but my hope is that this is just clear to you just from what I call the pictures, just from the fact that you know the behavior of the exponential function, and you know that e to the x kills anything, right? So 1 over e to the x for sure kills any polynomial because it just grows faster, right? It grows faster. You could have r to the 10 million here. It doesn't matter. It would still be killed by this thing as r goes to infinity. Yeah. So this thing goes to 0. This thing goes to 0. It's just the behavior of the graph. So what we have left is minus 1. Yeah. Do we believe that we have the right sign? Is negative the right sign? Well, let's think about it. So this guy right here, as we go from 0 to minus infinity, e to the x is always positive, but this guy is indeed negative. Yeah? This guy is indeed negative. So the graph of this function, graph of x e to the x, when x is equal to 0, it's 0. Yeah? But then for every x less than 0, it's got to be negative. Yeah? So initially, this will go down a little bit, but then it's going to go more and more towards 0. Yeah? This is the thing that we're calculating. So negative actually is the right answer. So commonly, we're naturally thinking about the area underneath the graph as being positive because that's the simplest examples, but it's just asking us for the integral, the signed area underneath the graph, and indeed negative is the correct thing. Yeah? But it's a good thing to do, to check at the end of your calculation if you believe the sign is correct. Yeah, in this case we do. Okay. Everybody with me? Everybody happy? Give me a thumbs up, those few of you I can see. Good. So, recap the steps. What do? We looked at this thing. We thought about how e to the x behaves. Yeah? And then we concluded we expect this thing to actually converge because it's going to 0 incredibly fast as r goes towards negative infinity. Yeah? And then we did the calculation, and it turns out that we get a finite answer, and that's confirming what our picture tells us should happen. Yeah? So in multiple choice, there is no mercy if you make a little calculational error and get the wrong answer, even if you have a good understanding. Yeah? So it'll be very much worth your while to have this way to verify if your answer makes sense by first having the intuition of whether or not you believe the thing converges or not. Okay? And I claim that your intuition, if you think a little bit about what e to the x is like, would give you that answer. Okay? And it's a special case of this principle that x, e to the x, as x goes towards negative infinity, is indeed going down to 0 a lot faster than 1 over x. Possibly faster than 1 over x. You see what I mean? All right, cool. Let's erase the board, do some more examples. Okay, let's do another one. Well, before we do another one, let's talk about comparison theorem. So we've been using this implicitly, but let's just state this. So suppose we have following notation with f on top is less than g is less than 0, and we have that if the integral from some number a to infinity f of x dx converges, in other words, it's a finite integral, so it's finite area underneath this graph. This implies that the integral from a to infinity g of x converges. Right? It's just immediately clear from the picture, right? So we have whatever number a, right? And we have f is lying above, right? So if this guy is g, then if the area underneath the graph from a to infinity for our function f is finite, then for sure it's true for g, just because it's underneath the graph, yeah? So that is true. And it's also true that if we integral from a to infinity and g of x dx diverges, this implies the integral from a to infinity f of x diverges. And again, it's just instantly clear from the picture. So if the area underneath the graph of g is infinite, then the area underneath the graph of f is infinite as well, right? Because it lies on top. Yeah? So we've been using this principle without explicitly stating it, but now we explicitly state it. And this sometimes is essential for us to answer some of these questions. Particularly when the question is about whether or not the thing converges rather than what the actual integral is. And you'll sometimes see questions of this form. So this is example 9. Show that integral from 0 to infinity e to the minus x squared dx converges. Okay, so important hint that we're using the convergence theorem is that it's not asking us what this answer is, what this actual integral is. Okay, and if you try and figure this out, you'll have difficulty because we can't easily find an antiderivative to this expression here. Yeah, the techniques we've taught you will make that very hard to answer. Later, we'll teach you about Taylor series, and this actually will be a question you could answer, but you can't answer it at this point. Okay. But it doesn't ask you what the answer is. It asks you just whether or not it converges. Do you believe it converges? Well, the question implies that it does, but give me a reason why you expect it to converge. Very good, yeah. Good, keep going. Can you add to that? You're exactly right. You're exactly right. Can anybody jump in, add some details to that? Right, perfect. This guy goes to 0 faster than 1 over x to the p, actually for any p, right? Any p at all. Take p to 1,000,000, this guy is going to beat it ultimately, yeah? Yeah, because again, e to the x is incredibly fast growing. If we have e to the x squared, it's growing even faster, yeah? Yeah. So yes, it's just going to 0 very fast, and we can be explicit about that. It's going to 0 faster than, say, 1 over x squared for all sufficiently large x. Yeah? You see what I mean, people? So we do indeed expect it to converge. And using this principle here, all we'd need to do is to find a function that lives above it that does converge. Yeah? And elaborating a little bit more, Convergence just cares about whether or not this integral is finite as the limit goes to infinity for a type 1, right? So if we just consider the integral from some number to infinity and that thing is fine, yeah? Since this guy is a perfectly nice function that has no vertical asymptotes, it's continuous, whatever, it's bounded. If we just know, for example, that the integral from 165 to infinity converges, then this entire thing converges. Yeah? Yeah? Just again the pitches, because convergence is about whether or not the area underneath the graph is finite, right? So for this guy here, it's always going to be bounded, right? It's never going to blow up or anything like this. It's always less than 1, right? So if we just consider from 165 onwards, and we know the area underneath the graph is finite, then for sure the area underneath the graph of this thing is finite, yeah? So if we know that from some point onwards, this guy lies underneath a function that is converging, then we're all set, yeah? Yeah? Cool. All right. So to answer this question, we can just find a function which converges where this guy is underneath it from some point onwards. And we could choose x squared, right? We could choose x squared. We could choose x to 1 over, start again. We could choose 1 over x squared. We could choose 1 over x to the 156 million, yeah? We could choose any power of x at all because ultimately this thing is going to be underneath it. Because that's how quickly e to the x grows, right? And e to the x squared grows faster. However, the simplest choice, it will be just to take 1 over e to the x itself. Because that thing we can calculate, yeah? And this guy will be less than 1 over e to the x for all x bigger than or equal to 1. Yeah? So, solution. We expect it to converge. I think this is very faint, this pen. And note that for x bigger than or equal to 1, then e to the x squared is bigger than or equal to e to the x. Yeah, because x squared is bigger than 1. Sorry, x squared is bigger than x for all x bigger than 1. So that's definitely true. Yeah. So that implies that 1 over e to the x is indeed going to be bigger than 1 over e to the x squared. Yeah? And we can integrate this guy, 1 over e to the x. It's just the integral from 1 to infinity, e to the minus x, which is the limit as r goes to infinity of the integral from 1 to r e to the minus x dx, right? And then what's this? This is the limit as r goes to infinity, antiderivative. Antiderivative of this guy is going to be minus e to the minus x like this. So this is the limit as r goes to infinity. Pull out the minus sign over here. We're going to have this minus e to the minus 1, like this. Yeah? And as r goes to infinity, this thing goes to 0, so this will just be e to the minus 1. Everybody with me? It's starting at 1 in this case, and that's the thing I was just saying over here. Thank you for this question. So we need to have a guy that lives above 1 over e to the x, yeah, in order to apply this comparison principle. And it's only true for x bigger than 1. It's only true for x bigger than 1, right? So we're going to be able to show that this thing converges to some quantity, yeah. So this implies that the integral from 1 to infinity, 1 over e to the x squared, converges. Right? Yeah? And agreed. The question was, what about the integral from 0 to infinity? But this is stuff I was talking about here. So we don't mind starting at some different point, because if we start at some different point and we know that, say, from 165 onwards, the integral converges, the stuff before it is finite, because this is just a bounded function integrated over a bounded interval. So there's no way there can be infinite area for this guy from 0 to 1. Does that make sense to you? Thank you for the question. Yeah. So we can make our life simpler by not starting from 0, but starting from 1, because if we start from 1, there's an easy candidate for a function that lives above our function that we can easily explicitly integrate, explicitly calculate. Yeah? Yeah? So we know that this thing converges, and since when we just can think about e to the minus x squared, yeah, this is always less than or equal to 1. Yeah? So the integral from 0 to 1, e to the minus x squared dx, it's a positive function, right? This thing is always just less than 1, right? This function is less than 1, we're integrating it from 0 to 1. Yeah? Yeah? So this is 1. This is our function, right? So this area is less than 1 times 1, yeah? So this is less than 1. Yeah? So putting these two things together, the fact that this is less than 1 and this guy converges, in fact, since we've made this calculation, we even know that this thing is less than e to the minus 1. Yeah? So putting this thing, let's call it star, and star together, we have that the integral from 0 to infinity e to the minus x squared dx is less than the part from 0 to 1 plus the part from 1 to infinity, so it's less than 1 plus e to the minus 1. Yeah? So for sure, this thing converges, it's got finite area. In fact, we have even more information. We know an upper bound on how big this area has to be. Right? It can't possibly be bigger than this quantity. Okay. So this is an important point, that it's useful to start at some other point where we know the function is underneath some other function that we can calculate. And what I was saying at the beginning is that we could choose a different function. We could choose 1 over x to the power 175, whatever. Yeah? Because ultimately, for large enough x, 1 over e to the x squared will be less than 1 over x to the power 175. And then we could compare the integrals from that point onwards. Yeah? And we'd have the same strategy would work. It just happens that comparing it to 1 over e to the x is just easier, because we see rather easily when 1 over e to the x is bigger than 1 over e to the x squared. Is everybody with me here? Give me a thumbs up if you're with me. Good, thank you. All right, let's do some more. Example 10, what about this? Integral from 1 to infinity, 1 plus e to the minus x over x dx. Solution. Let's use the principles we've been talking about. Firstly, do you think it's going to converge? Think about the graph of this function. Picture it in your mind. And then compare it to the cutoff function, the critical guy, which is 1 over x, right? How does this thing decay? How does it decay? What's the important thing about its decay? Very much like a 1 over x decay. How do we know that? What makes you say that? Perfect. Thank you. If we rewrite this, what's this? This thing on the top is just 1 plus an increasingly small number, right? Yeah? So if we look at this thing, I mean, for x bigger than whatever, 100, then this is between 1 and e to the minus 100, which is incredibly small, right? Yeah? Yeah? And in particular, it's always going to be bigger than 1 over e to the x. Yeah? Yeah? So it's decaying like 1 over x, and it's actually bigger than 1 over x. It is actually quite conveniently set up because this is true for every single x bigger than 1, right? Bigger than or equal to 1. So straight away we can just apply the comparison principle, and we know that this thing is bigger than or equal to this thing, right? Which diverges. I should say which diverges. Yeah, so in pictures, if this thing is the graph of 1 over x, then the guy we're interested in is just a little tiny bit bigger than that, and it gets closer and closer to it incredibly quickly. But it's always bigger, no? So for sure, the area underneath this thing cannot converge. Yeah? So if you visualize what this thing is like and you think about its decay, you really quickly come to the answer. If you just try and calculate this straight away, you can do it. You can do this. You can do this calculation, but it's going to be a pain. It'll take you, whatever, 5 to 10 minutes, and you could get it wrong. You could get it wrong. So what I'm going to try and emphasize to you is this thing I'm emphasizing throughout, that we're going to think of the pictures as our first thing. We're going to think about what these things mean before we start to calculate. And then we calculate just to confirm it. And in this case, there's no need to, because it's just true by this principle. It's just answerable by this principle we've talked about. Yeah? So diverges. What about this? What if we had this? Would this thing converge? Would this thing converge, people? It'll be lower, indeed, but will it be, how much lower will it be? Perfect, good. That's good. Let's express your thought in the language of maths, right? So e to the minus x goes towards 0. This is exactly what you said in words in the language of maths. As x goes to infinity, right? Yeah. And in fact, it's decreasing towards 0. Yeah. So for some particular number, let's say r, we have for sure that e to the minus x is less than 1 over 2 for all x bigger than or equal to r. What have I done? I've expressed in the language of maths that this function e to the minus x goes towards 0, right? And at some point it is less than a half, right? All I've done is express in language of maths this picture that you all believe, that you can all see. Yeah? In fact, we know what this r is, right? Because if we just set these things to be equal, if we just have e to the minus x is equal to a half, we try and find the exact point where it crosses, right? That's the same as saying that 2 is equal to e to the x, which is the same as saying that log 2 is equal to x, right? So from this point onwards, e to the minus x is less than a half. Do you see what I mean? Give me a thumbs up if you do. Yeah? We don't actually care what the value is, but it's nice to have one just to make sure. Yeah? Yeah? So if we instead consider the integral from log 2 to infinity, 1 over e to the minus x over x, right? We know that this stuff above, the stuff above is going to be bigger than a half. Yeah, the stuff in this red brackets. Yeah? Because e to the minus x is less than a half. So 1 minus something less than a half is bigger than a half. Yeah? So this thing is bigger than the integral from log 2 to infinity of 1 over 2x. Yeah? And then this is, just pull out the half, and then this is the integral from log 2 to infinity, 1 over x dx, and that thing is infinite, yeah? Which diverges. Yeah? So the answer that the last student gave me is right. And all I did here is express his thought in the language of maths. Yeah? And that conclusively nailed down the issue. Yeah? Because the area underneath this graph from log 2 to infinity is infinity. Yeah? So for sure, this thing, which is the integral from 1 to infinity, which has to be bigger than integral from log 2 to infinity, because this is positive all the time, yeah, has to be infinity as well. Do you see what I mean? Okay, good. So we profit a great deal from thinking about how things decay before we calculate. And we can get the answer with very high reliability, in fact, more reliability than just calculating, if you calculate like me. All right, so let's see if we do another one. How are we time? 5 minutes. Okay, let's try and squeeze in one more question then. Question 7. So this is from the end of the section, and at the end of the section, it gives us a whole bunch of integrals, and it says, does the integral converge or not? And if it converges, calculate what the integral is. So this is our integral. This is 1 to infinity, 1 over x squared plus x dx. I'm going to erase the board while you look at this and you try and apply the principles of relearning to figure out whether or not this thing converges. And then once we have an answer as about whether or not this thing converges, then we'll try and calculate it. So the issue, it goes towards 0. It goes faster than 1 over x. Yeah? It goes faster than 1 over x. That's the issue. You see what I mean? Yeah, this guy's going to go faster than 1 over x. In fact, what will this guy go faster than? What can we compare this guy to for all x, 1 over x squared, right? This thing is less than 1 over x squared for all x bigger than or equal to 1. Yeah, in fact, for all x bigger than or equal to 0, but we're only interested from 1 to infinity. Yeah? So this guy is going to 0 underneath the graph of this guy. Yeah? So it's going fast enough. Yeah? So probably that's what you meant when you said it goes towards 0, but the real crux is that it's going towards 0 fast enough. Huh? And fast enough it is because we see this power 1 over x squared underneath, yeah? Cool. Even if we had a minus, for the reasons I argued previously, it would still be going to 0 fast enough. We have a plus. So we expect this thing to converge. We expect this thing to converge. So we should be able to calculate it, yeah? We should be able to calculate it. So we calculate now. All right, so I have 2 minutes. Probably I'm not going to get the calculation done in 2 minutes. We'll give it a go. Feel free to leave when you want to. All right, so expect it to converge. Or actually, we know it's going to converge. Okay, but now we're going to try and calculate it. So we need to calculate from 1 to capital R of this thing. What method are we going to apply to explicitly calculate this? Now we're experts on doing integration, right? We've learned a whole bunch of techniques. We look at this, we go, okay, this is a rational function. We know what to do. Yeah? We know what to do. Yeah? Because notice that 1 over x squared plus x is a rational function. It's a proper rational function. Oops. Yeah. So then we have 1 over x squared plus x. Let's write this like this, x plus 1. So which case are we looking at here? What case is that? Case 1, right? We have distinct linear factors. So this is equal to a over x plus b over x plus 1. We make a common denominator, a over x plus 1 plus b over x plus 1. Yeah? And then this implies that 1 is equal to a over x, a times x plus 1 plus b times x, which implies that, or which is equal to a plus b times x plus a. And since this is true for all x, I'm doing this fast, but we know how to do this kind of stuff. We practice this a lot, right? So then this implies that a is equal to 1, because we're comparing the constants. And comparing the x terms, we have 0 x term here. So this also implies that a plus b is equal to 0. So therefore, b is equal to minus 1. Yep. So our partial fraction decomposition is that 1 over x squared plus x is the same as 1 over x minus 1 over x plus 1. So then we can do this integral here. Let's call this thing star. So star is equal to the integral from 1 to r of this thing, 1 over x minus 1 over x plus 1 dx. Excuse me a second. And then what is this? This is log absolute value of x minus log absolute value of x plus 1. Yeah. And what's this? This is log of r. Log of 1 is 0, so there's nothing there. And we have log of r plus 1. Yeah. And then minus log of 2, so it's plus log of 2. Yeah. So we put the brackets around here. Yeah. We'll have log of r plus 1 minus log of 2, but then it's minus, so it's therefore it's plus. Yeah. Cool. All right. So our original integral down here, let's call this thing star. So star is equal to the limit as r goes to infinity of log of 2 plus log of capital R minus log of r plus 1. Yeah? Now, do we have a problem? Because log of r goes to infinity, log of r plus 1 goes to infinity. So how are we going to figure this out? So not earlier, but the other day, someone asked me about why don't we just plug in infinity, and that's this is why, because infinities don't cancel each other out. So, I mean, suppose we had something like this. Suppose we had that the limit as x goes to infinity of x squared minus x. I was trying to come up with something which looks more like this, but let's look at this. Huh? If we broke this up, this would be the limit as x goes to infinity of x squared minus the limit as x goes to infinity of x. And both of those are infinity, so infinity minus infinity, right? Yeah. And that thing that's not the answer. So that if we cancel the infinities, we'd say this was 0. But that's definitely not 0, because this is the same thing as x minus 1, right? And we see from this, right, that definitely this is going up to infinity, right? So the answer is actually infinity, not 0, as you would think if you could cancel the infinities. So that's one of the reasons we emphasize all the time not to do arithmetic with infinities. That's the reason for doing this capital R stuff and taking the limit as R goes to infinity. So I'm very glad you said that. Thank you for saying that. But that's not what we're allowed to do. Back to this thing. So we can't just take the limit and cancel this thing. So if you look back in your limit laws, you can add and subtract limits when the limits exist, which means they exist as a number, right? This you cannot do, so wrong answer. Actually, when I was talking with the student who asked about this, I said that in the early development of calculus and modern mathematics, people weren't so clear about this, weren't so clear about that infinity is not something you can treat as a number. And if you do mix that up, you can quite easily, quite convincingly come up with wrong answers, much more convincing than this. So the start of mathematical rigor, of being very precise about what you mean and what you're doing, was precisely because you can go completely astray unless you really nail down every single concept you're dealing with and only do things that are valid for the concepts you're working with. So yeah, that's why we spend so much time talking about concepts and what they mean and why and what is true and not true, and we talk about theorems, things that we know are true for sure. Yeah. All right, back to this. So we have something to think about, because as R goes to infinity, this goes to infinity and this goes to infinity. We can't cancel them. We can't take the limit through. Yeah. So how should we understand this? Perfect. Thank you. Yes, we can use limit laws. So this 2 we just pull out because it doesn't involve R. And then this is plus the limit of R goes to infinity of log of R over R plus 1, just by limit laws, right? Yeah, because log of A plus B, log of A times B is log of A plus log of B, right? Log of A over B is log of A minus log of B. These are the limit laws we learned back in the day, yeah? Cool. Now look at this. What's the limit? What's the limit now? What's this thing R over R plus 1 tending towards? Right? So what's the limit of the overall expression? 0, yeah? Because that's what you learned in Calc 1, that if you have a continuous function, right, and you have something that's tending towards something inside it, right, and if it's continuous, that means you can take the limit outside, take the limit of the function acting on the thing, and that'll be equal to the function acting on the limit, yeah? So look back at that if that doesn't make sense to you. You can just, as I would rather do all the time, you can just visualize it, right? So you know that log looks like this, right? Think about R over R plus 1, right? It's some number which is a bit less than 1, but it's getting closer and closer to 1, yeah? So if you plug in that number into log, you can see it's going to get more and more towards 0. You can just see it, yeah? You can just see it. Rather than apply a general principle, you can just see that this thing is going to tend towards log of 1, which is actually 0. Yeah? So this thing is just log of 2, and that's the answer. Do we agree with the sign? Is the sign positive? Yes, we do, right? Because this is a positive function. So we have a positive answer, so we believe it's the correct sign. Yeah? And this is actually the correct answer. Cool. Is everybody happy? All right, super. Good. So main takeaway is we look at something, we think about its growth or its decay, if it's type 1. Yeah? We try and understand whether it'll converge or not based on that. And then we do the calculation, which should confirm what we were thinking previously. Yeah? Cool. So if you practice this, you'll feel very comfortable with this pretty quickly. All right, that's it for today. Have a great weekend. Bye-bye, people.